Look up at the night sky, beyond the familiar constellations and the scattered glow of distant stars. For centuries, we've gazed into that darkness believing we understood what was out there. Galaxies full of light, swirling with stars, cosmic beacons illuminating the void. But what if I told you that some of the most massive structures in the universe are almost completely invisible? That there are entire galaxies hiding in plain sight, made not of stars and dust, but of something far stranger and more unsettling. These are the dark galaxies, cosmic phantoms that defy everything we thought we knew, and even the most brilliant scientists speak of them with a mix of awe and genuine caution. Imagine a galaxy so enormous it dwarfs our own Milky Way, yet it emits almost no light. It doesn't glow, it doesn't shimmer, it looms in perfect silence, a ghost in the machinery of the cosmos. For decades, these dark galaxies were little more than theoretical possibilities, but today, advanced telescopes and deep space observations have revealed something startling. They're real. And they're everywhere. These are not mere holes in space. They are massive, structured, and gravitationally powerful, holding the keys to mysteries we are only beginning to grasp. Why do they exist? What are they made of? And why does their very presence challenge the foundations of modern astronomy? This is a journey into the shadows of the universe, a voyage to the edges of understanding, where certainty gives way to wonder, and wonder slowly bleeds into unease. We're about to explore 25 dark galaxies that have left researchers questioning the nature of reality itself. From colossal structures that bend the laws of physics to silent giants that may rewrite cosmic history, each of these enigmas pulls us deeper into a story far grander and far darker than we ever anticipated. So join me as we step into the unknown and uncover why some discoveries in the cosmos are as thrilling as they are deeply, profoundly mysterious. Our journey into the shadows begins with a galaxy so faint it was hidden in plain sight for decades, camouflaged within the well-known Coma cluster. This is Dragonfly 44, and its discovery in 2015 sent ripples through the astronomical community, not for what it contained, but for what it almost completely lacked. Imaged by the unique Dragonfly telephoto array, an instrument literally built from repurposed camera lenses designed to see the faintest, most diffuse light in the universe, this galaxy appeared as little more than a faint smudge, a cosmic ghost. Yet this phantom held a staggering secret, one that would redefine our understanding of what a galaxy even is. At first glance, Dragonfly 44 seems almost boring. It's a large galaxy, roughly the size of our own Milky Way, but it contains a mere 1% of the stars. Imagine our brilliant spiral home galaxy with its hundreds of billions of suns. Now remove 99 out of every 100 stars. What remains is a desolate, incredibly sparse distribution of stars, so spread out that the galaxy is virtually transparent. If you were inside Dragonfly 44, the night sky would be nearly black, with only a few distant, lonely suns punctuating an endless, empty darkness. This is why it's classified as an ultra-diffuse galaxy. It has an extremely low surface brightness, making it incredibly difficult to detect against the blackness of space. But here's where the mystery deepens into something truly profound. Despite having almost no visible matter, the stars that do exist within Dragonfly 44 are moving at astonishingly high velocities. This was the key clue. By measuring the speed of these stars, astronomers could calculate the gravitational force required to keep them from simply flying off into intergalactic space. The result was mind-bending. The mass required to bind this wispy ghost of a galaxy together is enormous, comparable to the mass of our entire star-rich Milky Way. This means Dragonfly 44 has roughly the same mass as our galaxy, but 99.99% of that mass is completely invisible. It is, for all intents and purposes, a galaxy made almost entirely of dark matter. This revelation is what makes it a terrifying anomaly. According to our standard models of galaxy formation, a structure with the mass of the Milky Way should have attracted and accumulated enough gas to form a correspondingly huge number of stars. Dragonfly 44 completely defies this logic. It has the mass of a giant but the stellar population of a dwarf. It's a cosmic paradox, a heavyweight ghost. This forces scientists to ask unsettling questions. Did something prevent its gas from collapsing into stars? Was it stripped away by some violent event? Or does its existence point to a fundamentally different, unknown way that dark matter can clump and structure itself, forming invisible scaffolds upon which only a handful of stars dare to cling? Dragonfly 44 isn't just an oddity, it's a direct challenge, a silent question mark hanging in the void. If Dragonfly 44 represents a ghostly giant, then our next subject is its ancient, diminutive cousin, a cosmic fossil that has survived virtually unchanged since the dawn of time. This is Segue 1, a tiny, ultra-faint dwarf galaxy that orbits our own Milky Way. Discovered in 2006 in data from the Sloan Digital Sky Survey, it appears as little more than a sparse sprinkling of stars against the dark canvas of space. With a total luminosity of only about 300 times that of our Sun, it is one of the faintest galaxies ever detected. Yet, this unassuming collection of stars holds a secret of staggering proportions, making it one of the most extreme and dark matter-dominated objects ever found. The true nature of Segue 1 reveals itself not in the scant light it emits, but through the frantic motion of its few hundred stars. When astronomers measured their velocities, they were met with a result that defies simple logic. These stars are whipping around at speeds that should tear the entire structure apart. The only force powerful enough to hold them together is an immense gravitational anchor, a halo of dark matter of unbelievable density. The calculations point to a mass-to-light ratio that is almost incomprehensible. For every single bit of light its stars produce, there is over 3,000 times more mass in the form of invisible dark matter. This ratio is among the highest ever measured, meaning Segue 1 is essentially a lump of pure dark matter with a few accidental stars caught in its grip. This extreme characteristic transforms Segue 1 from a mere dwarf galaxy into a pristine relic, a window directly into the universe's earliest epochs. Its stars are incredibly ancient, composed almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang. The absence of heavier elements suggests that Segue 1 experienced very few, if any, periods of star formation after its initial birth. It is a cosmic time capsule, a frozen snapshot of what the very first galaxies looked like over 13 billion years ago. It never evolved, never grew, and never enriched itself. It simply persisted in a state of arrested development, preserved by its isolation and its overwhelming dark matter content. This leads scientists to two compelling and equally fascinating theories about its origin. The first posits that Segue 1 is a genuine failed galaxy. In this scenario, it began collapsing from a cloud of primordial gas and dark matter just after the Big Bang. But for some reason, perhaps because it was stripped of its gas by a larger neighbor or simply resided in a barren patch of space, the process of star formation was abruptly and permanently halted. It had all the dark matter needed to become a major galaxy, but only managed to form a handful of stars before its growth was stunted. The second, even more dramatic theory suggests that Segue 1 is not a failed galaxy at all, but the surviving core of something far grander. It could be the remnant nucleus of a much larger dwarf galaxy that was almost completely torn apart by the immense tidal forces of the Milky Way. Over billions of years, our galaxy's gravity would have shredded away its outer stars and gas, leaving behind only its incredibly dense, dark matter-rich heart. This would make Segue 1 a celestial survivor, the enduring heart of a vanquished system that now tells a story of cosmic violence on an epic scale. Moving from the ancient relic of Segue 1, we encounter another enigmatic neighbor, Triangulum II, a faint dwarf galaxy that presents a puzzle wrapped in darkness and illuminated by a mysterious, energetic glow. Situated close to our Milky Way, this unassuming collection of stars was once thought to be a rather typical ultra-faint dwarf. But further scrutiny revealed something far more peculiar happening at its core, transforming it from a simple celestial object into a potential beacon for one of physics' greatest quests, the direct detection of dark matter. The intrigue around Triangulum II centers on a powerful and unexpected signal, a surge of gamma radiation that some scientists believe could be the long-sought signature of dark matter particles destroying each other in a violent final act. Like Segue 1, Triangulum II is incredibly faint and difficult to observe, with very few stars to mark its presence. Yet the motions of those few stars tell a familiar story of overwhelming, invisible mass. Measurements indicate the stars are moving at velocities that demand a gravitational force far exceeding what the visible matter could possibly provide. The calculated density of dark matter within Triangulum II is astonishingly high, ranking it among the most dark matter-dominated objects known in the local universe. This immense concentration of invisible mass in such a small volume is the first crucial ingredient in this cosmic mystery, setting the stage for the even more dramatic discovery that followed. The plot thickened dramatically when astronomers studying data from NASA's Fermi Gamma-Ray Space Telescope noticed something extraordinary. Emanating from the precise location of Triangulum II's center was a significant excess of high-energy gamma-ray photons. This wasn't just background noise, it was a concentrated spike of energy right where the dark matter density was predicted to be at its absolute peak. This correlation immediately sparked intense excitement, as one of the leading theoretical explanations for such a signal is dark matter annihilation. The idea is that dark matter particles, which we believe are their own antimatter counterparts, could collide with one another. When they do, they would annihilate in a flash of energy, converting their mass directly into other particles, including gamma rays. If confirmed, the signal from Triangulum II would represent the first ever indirect evidence of dark matter's particulate nature, a monumental breakthrough in our understanding of the universe's hidden architecture. However, in science, extraordinary claims require extraordinary evidence, and the gamma-ray excess from Triangulum II is hotly debated. The central question is whether this energetic glow truly comes from dark matter annihilation, or if there is a more conventional, albeit still fascinating, astrophysical explanation. One compelling alternative theory suggests that Triangulum II might not be a pristine, intact dark galaxy at all, but rather the tidal remnant of a larger system that was torn apart. In this scenario, the gravitational tides of the Milky Way could have stripped away stars and gas, leaving behind only the dense, dark matter-rich core. The gamma-ray signal, then, might not be from annihilating dark matter, but could instead be produced by a population of rapidly spinning neutron stars known as millisecond pulsars. These incredibly dense stellar corpses can emit powerful beams of gamma radiation, and a cluster of them lurking unseen in the galaxy's center could perfectly mimic the anticipated signal of dark matter. This scientific debate highlights the delicate and complex nature of hunting for the invisible. Triangulum II sits at the crossroads of two equally thrilling possibilities. It could be a unique laboratory, offering us a front-row seat to the fundamental physics of dark matter annihilation, a process that could reveal what makes up 85% of the matter in the cosmos. Or it could be a stark reminder of the universe's violent dynamics, a celestial ghost that is the surviving evidence of a dramatic disruption billions of years in the past. For now, it remains an enigmatic and powerful source, its true nature locked away, challenging our instruments and our intellects as we strive to listen to the secrets it whispers in gamma rays. But as we pull our gaze back from the intense, energetic mystery of Triangulum II, we encounter a ghost of an entirely different nature, one defined not by what it emits, but by its profound and almost absolute silence. Drifting through the halo of our own galaxy is Antlia II, a behemoth cloaked in shadows, discovered in 2018 within data from the European Space Agency's Gaia mission. This galaxy is a paradox of scale. It is roughly the same size as the Large Magellanic Cloud, one of the most prominent satellite galaxies of the Milky Way, but its light is spread so thin that it evaded detection for decades, earning it the title of one of the most diffuse objects ever discovered in the cosmos. If you were to somehow place Antlia II next to our own brilliant Milky Way, it would appear as little more than a faint, ethereal wisp, a cosmic smudge against the blackness. The sheer difficulty in spotting Antlia II cannot be overstated. Its stars are so few and so widely dispersed that their combined light creates a surface brightness hundreds of times fainter than the natural glow of Earth's own night sky. It's like trying to spot a single, dim light bulb from miles away while standing in the middle of a brightly lit city. This incredible faintness is why it took the precise, all-sky mapping capabilities of the Gaia satellite to finally tease its signal out from the background. Gaia didn't just take a picture, it meticulously tracked the subtle, collective motion of stars, identifying a group moving together through space that was otherwise completely lost in the stellar crowd. This was the ghostly signature of Antlia II, a vast structure revealed not by its light, but by its synchronized dance through the galaxy. Here lies the core of the mystery that has astronomers so captivated and perplexed. A galaxy of this immense physical size, one that rivals other major satellites of the Milky Way, should, according to all established models of galaxy formation, be brimming with stars. It had the raw material and the gravitational potential to become a shining landmark, yet it failed spectacularly. This presents a profound challenge to our understanding of how dark matter behaves and structures itself. The prevailing theory of cold dark matter suggests that it should form dense, clumpy halos that act as gravitational seeds for galaxies. Antlia II's halo appears to be strangely fluffy and extended, far less concentrated than our models predict. Its dark matter seems to be distributed in a way that prevented the gas from collapsing efficiently to form stars, leaving behind a dark, sprawling giant. Scientists are now grappling with several compelling theories to explain this cosmic anomaly. One possibility is that Antlia II is the victim of intense and repeated stellar feedback. In its early history, perhaps the first few generations of massive stars went supernova. These violent explosions could have blown the remaining star-forming gas clear out of the galaxy before it could collapse to create new suns, effectively sterilizing it and halting its development. Another, more dynamic theory suggests that Antlia II has endured a dramatic and violent history with the Milky Way itself. Its wide, looping orbit may have brought it crashing through the disk of our galaxy multiple times over billions of years. Each passage would have subjected it to immense tidal forces, gravitational shocks that could have ripped away its gas and stars, stretching it out and puffing up its dark matter halo into the diffuse phantom we see today. This makes Antlia II far more than just another oddity. It is a living challenge to our cosmological models. Its very existence forces us to ask whether our understanding of dark matter's fundamental properties is incomplete. Perhaps dark matter can interact with itself in ways we haven't yet accounted for, preventing it from forming the dense cores we expect. Or Antlia II could be the key evidence for a new class of galaxy, one that formed in a uniquely quiet, undisturbed pocket of the early universe, evolving on a path entirely its own. It stands as a silent, looming question mark in our own backyard, a reminder that some of the universe's deepest secrets are hiding in the darkest and most unexpected places. Just when we thought we were beginning to understand the rules, the universe presented us with an anomaly so bizarre it seemed to break them entirely. While astronomers were growing accustomed to the idea of galaxies dominated by dark matter, the discovery of NGC 1052 DF2 did the unthinkable. It appeared to have none at all. This wasn't a dark galaxy, it was a ghost of a different kind, a cosmic paradox that directly challenged the very framework we use to explain the universe. Its identification sent a seismic shock through the world of astrophysics, igniting a fierce debate that continues to this day, forcing us to ask a terrifying question: what if our most fundamental assumptions are wrong? The story begins in 2018 with a team led by astronomer Pieter van Dokkum using the Dragonfly telephoto array. They were studying a region around the elliptical galaxy NGC 1052 when they spotted something peculiar. Designated NGC 1052 DF2, this object was classified as an ultra-diffuse galaxy, similar in size to the Milky Way but containing only about 1/200th of the stars. Its ghostly, almost transparent appearance was strange enough, but the real bombshell came when the team measured the velocities of 10 bright star clusters orbiting within it. The laws of physics tell us that the speed of these orbiting clusters is determined by the gravitational pull of the mass inside their orbit. In virtually every other galaxy ever studied, the stars and gas account for only a tiny fraction of that mass. The rest is the unseen hand of dark matter. But in DF2, the math told a completely different story. The star clusters were moving surprisingly slowly. Their sedate pace indicated that the total mass pulling on them was almost exactly equal to the mass of all the visible stars they could see. There was no extra gravitational pull, no missing mass, and seemingly no dark matter. This result was so revolutionary it was met with widespread skepticism. Finding a galaxy without dark matter was like finding a river without water or a forest without trees. It contradicted the foundational model of how we believe all structures in the universe form. Dark matter halos are supposed to be the gravitational seeds that draw in gas, allowing galaxies to coalesce in the first place. A galaxy without this scaffold shouldn't exist according to the theory. DF2 wasn't just an oddity, it was a direct challenge to a core principle of modern cosmology. Naturally, such an extraordinary claim triggered a wave of follow-up studies, and the controversy quickly deepened. One of the most significant counter-arguments centered on the distance to the galaxy. Distance is a critical measurement in astronomy. Get it wrong, and all your other calculations, including mass, will be incorrect. The initial study placed DF2 at a distance of 65 million light-years, associating it with the NGC 1052 galaxy group. However, another team, using a different method with the Hubble Space Telescope, argued the galaxy was much closer, only 42 million light-years away. This shorter distance would mean the galaxy is intrinsically smaller and dimmer, and its star clusters would be less massive. If true, the slower motions of the clusters could be explained without needing to invoke a lack of dark matter. The visible mass alone would be sufficient to hold them. The debate over this single number became a central battleground in determining the galaxy's true nature. Other researchers proposed different explanations. Perhaps DF2 is not a pristine, isolated galaxy, but a tidal dwarf galaxy. These are rare objects that form not from a collapse within a dark matter halo, but from gas and stars ripped out during a violent collision between two larger galaxies. This gas, already stripped of its dark matter, could later collapse to form a new galaxy, one born without a dark matter foundation. If DF2 formed this way, it would be a fascinating cosmic orphan, but it would no longer pose a threat to the standard model of dark matter. It would simply be a beautiful exception that proves the rule. The implications of this discovery, if confirmed, are profound. The existence of even a few galaxies devoid of dark matter would provide powerful evidence that dark matter is a real, physical substance that can be separated from ordinary matter, rather than a misunderstanding of gravity itself. Some alternative theories, like modified Newtonian dynamics or MUND, proposed that there is no dark matter and that gravity simply behaves differently on large scales than Newton or Einstein predicted. Buttman struggles to explain a galaxy like DF2, where the motions of the star clusters appear to perfectly follow Newton's laws without any need for modification or extra mass. In a strange twist, a galaxy without dark matter actually strengthens the case that dark matter exists everywhere else. The story of NGC 1052 DF2 is a perfect example of the scientific process in action, a startling discovery, vigorous debate, and a relentless pursuit of better data. It reminds us that our models of the universe are living constructs, constantly being tested and refined by new observations. Whether DF2 is ultimately confirmed to be devoid of dark matter or explained away as a mismeasurement, its value is undeniable. It forces us to question, to re-examine, and to look deeper. It is a celestial provocateur, ensuring that our journey to understand the cosmos remains as dynamic and unpredictable as the universe itself. The intrigue surrounding seemingly dark matter-free galaxies only intensified with the discovery of another ghostly inhabitant of the same cosmic neighborhood. Lying near its controversial sibling, NGC 1052 DF4 presented astronomers with a second, equally perplexing puzzle. If DF2 was a challenge to our models, then DF4 was the universe doubling down, forcing scientists to confront the possibility that these weren't mere flukes but perhaps signposts to a deeper, more complex reality. This galaxy, also large and incredibly faint, appeared to tell the same startling story. A massive structure where the visible matter seemed to account for all the gravity, leaving no room for the dark matter we believe should be there. The evidence for DF4's missing mass came from the same method used for DF2, studying the motion of its stellar components. Researchers measured the velocities of its bright globular clusters, dense, spherical collections of stars that orbit the galaxy's center. Just as with DF2, these clusters were moving far too slowly for the amount of visible mass they represented. Their leisurely orbital pace indicated that the gravitational force holding them in place was incredibly weak, suggesting a total mass that was almost identical to the mass of the stars themselves. This result was a near-carbon copy of the DF2 findings, making it exponentially harder to dismiss the phenomenon as a one-off observational error or a strange coincidence. Two galaxies in the same group, both defying the most fundamental rule of cosmic structure, demanded a serious explanation. This repetition sparked a crucial debate within the astronomical community. Were these two objects genuine examples of galaxies that formed without dark matter, or was something else actively stripping the dark matter away? The most compelling theory to explain both DF2 and DF4 involves a violent and dramatic cosmic event, a gravitational showdown with their massive neighbor, the elliptical galaxy NGC 1052. This giant galaxy possesses an immense gravitational field, and the theory posits that both DF2 and DF4 ventured too close to it in the distant past. As they did, they were subjected to a process known as tidal stripping. Imagine the diffused dark matter halo of a small galaxy as a vast, invisible cloud surrounding its visible stars. As this galaxy passes near a much larger one, the intense and uneven gravitational pull, the tidal force, acts like a cosmic sieve. It can pull and stretch the dark matter, which does not interact with itself or other matter, effectively siphoning it away from the galaxy's core. The visible stars, being more concentrated and tightly bound, might remain largely intact. The result is a galaxy that still has its stars but has lost the majority of its dark matter anchor, perfectly matching the observations of both DF2 and DF4. This would make them not primordial anomalies but victims of a celestial robbery. However, the story took another fascinating turn with later observations of DF4. Some studies suggested that the galaxy was not just lacking dark matter, but was actually in the process of coming apart at the seams. Detailed images hinted that the galaxy's outskirts were being stretched and distorted, with stars seemingly being pulled away in long, faint streams. This was interpreted as the telltale signature of tidal disruption happening right now. It appeared DF4 was being torn apart by the very gravitational forces that may have already robbed it of its dark matter, adding a layer of tragic dynamism to its existence. It became a snapshot of a galaxy in its death throes, a fleeting cosmic structure being dismantled before our eyes. Yet, in a twist characteristic of this entire field, even this elegant explanation faced its own challenges. The debate over the precise distance to these galaxies continued to be a major point of contention. If the distances were wrong, the calculated masses would be wrong, potentially resolving the mystery without needing to invoke missing dark matter or violent stripping. Furthermore, the tidal stripping scenario itself requires very specific conditions to work. Could the same process have happened to two galaxies in the same group, producing such similar and extreme results? Some scientists argue it's possible, while others find it statistically unlikely, pushing them to consider even more exotic possibilities. The existence of DF2 and DF4 forces us to hold two equally revolutionary ideas in tension. On one hand, they could be stunning proof that dark matter is indeed a real, separable substance, demonstrating that it can be dynamically stripped away from normal matter under the right conditions. This would actually bolster the standard model of cosmology. On the other hand, if the evidence for their missing dark matter holds and the tidal explanation falls short, they could be the first evidence of a completely unforeseen pathway of galaxy formation, one that somehow bypasses the need for a dark matter halo entirely. This would require a fundamental rewrite of our cosmic playbook. These ghostly galaxies are more than just curiosities, they are critical natural experiments. They push our theories to the breaking point, compelling us to look closer, think deeper, and remain open to the universe's next great surprise. Leaving behind the contentious debate over missing dark matter, our journey takes us into the heart of one of the universe's most crowded and violent neighborhoods, the Virgo cluster. Here, amidst a chaotic metropolis of over 1,000 galaxies, we find VCC 1287, a galaxy that embodies quiet resilience in an environment of extreme forces. Unlike the puzzling voids of DF2 and DF4, VCC 1287 is a classic dark galaxy dominated by the unseen hand of dark matter. But its story is no less fascinating, offering a masterclass in how a galaxy's surroundings can dictate its fate, sculpting it into a faint, ghostly survivor. VCC 1287 is the very definition of an ultra-diffuse galaxy. It is large in physical size, yet its light is smeared so thin that it borders on invisibility. If you were to compare it to a bustling, star-forming spiral like our Milky Way, the difference would be stark. Our galaxy is a brilliant, dynamic whirlpool of gas, dust, and billions of stars. VCC 1287, by contrast, is a pale, ethereal wraith. Its population of stars is ancient and stagnant, with very few new stars being born. This lack of activity gives it a serene, almost fossilized quality, as if time within this galaxy has nearly stopped. It is a quiet backwater in a downtown urban core, a silent observer to the frantic collisions and interactions happening all around it. The environment of the Virgo cluster is key to understanding why VCC 1287 looks the way it does. Galaxy clusters are the most massive gravitationally bound structures in the universe, and they are notoriously harsh places for their inhabitants. The space between galaxies in a cluster is not empty. It is filled with a superheated, tenuous plasma known as the intracluster medium. For a galaxy like VCC 1287, moving through this searing hot gas is like running into a relentless, scorching headwind. As it orbits through the cluster, this pressure strips away its cold, neutral hydrogen gas, the very raw material needed to form new stars. This process, known as RAM pressure stripping, effectively suffocates the galaxy, shutting down its star-forming factories and leaving it with only the aging stars it formed long ago. But the violence doesn't end there. The immense gravitational pull of the cluster itself and the close encounters with other massive galaxies exerts another destructive force, tidal stripping. Just as the gravity of the Milky Way may have stretched and puffed up Antlia II, the collective gravity of the Virgo cluster tugs and distorts galaxies like VCC 1287. This can pull away not only additional gas but also stars from the galaxy's outer regions, further contributing to its diffuse, ghostly appearance. It's a celestial double assault, leaving the galaxy barren and extended. Here is where the plot deepens. Despite having had much of its visible matter stripped away, measurements show that VCC 1287 retains a surprisingly massive and dense halo of dark matter. The motions of its remaining stars indicate a gravitational force far stronger than the visible mass can account for. This reveals a critical insight into the different behaviors of dark matter and normal matter. The normal atomic gas was easily swept away by the hot intracluster wind because it interacts electromagnetically. The dark matter, however, feels only gravity and does not interact with the hot plasma or with itself. This means the galaxy's dark matter anchor remains largely intact, holding onto the skeletal remains of the visible galaxy, even as the cluster environment systematically dismantles it. This makes VCC 1287 a crucial case study. It is not a failed galaxy that never formed many stars. It is more accurately described as a quenched galaxy, one whose star formation was actively shut down by its environment. It demonstrates that the cluster itself is a powerful cosmic architect, capable of transforming galaxies into the dark, ultra-diffuse objects we see. By studying populations of galaxies like VCC 1287, astronomers can trace the history of a cluster's violence. Each ghostly galaxy serves as a fossil record, its structure and star content revealing the intensity and timing of the stripping processes it endured. VCC 1287 shows us that the pathway to becoming a dark galaxy is not singular. While some, like Dragonfly 44, might be born dark and massive, others are made dark through external forces. They are the celestial equivalents of ancient trees that have been weathered and shaped by relentless winds, their forms telling a story of survival against tremendous pressure. In the chaotic core of the Virgo cluster, VCC 1287 stands as a silent testament to resilience, a ghost shaped by its environment, holding fast to its dark secret at the center of the storm. Now we turn our gaze beyond our local group to our nearest major galactic neighbor, the magnificent Andromeda Galaxy. Orbiting this cosmic titan is one of its most enigmatic satellites, a ghost known as Andromeda 19. Discovered in 2006, this dwarf galaxy immediately stood out not for its brightness, but for its astonishing lack of it. Its stars are scattered across an immense volume of space, creating a structure so vast and tenuous that it pushes the very definition of what a galaxy can be. If you could hold it up to the Milky Way, you would find it spans a similar diameter, yet contains only about 1/1,000,000th the number of stars. It is a cosmic will-o'-the-wisp, a giant in physical scale but a phantom in luminosity. The profound diffuseness of Andromeda 19 tells a story written in gravity and motion. Astronomers studying the subtle movements of its sparse stellar population uncovered a now familiar signature. The stars are moving at velocities that betray the presence of a massive, unseen anchor. The gravitational force required to keep these widely separated stars from simply drifting apart into the void is immense. This means that despite its ghostly appearance, Andromeda 19 possesses a massive dark matter halo, a hidden gravitational engine that completely dominates its structure. This presents a fascinating puzzle for cosmologists, as the dark matter halo appears to be unusually extended and puffy, much like the halo of Antlia II. Its dark matter is not concentrated in a dense core but is instead spread out, which may be a key reason why so few stars ever formed within its grasp. The existence of such a large, dark matter-dominated satellite orbiting Andromeda provides a critical clue to understanding how giant galaxies are built. The prevailing theory of galactic formation, known as hierarchical clustering, suggests that massive galaxies like Andromeda and our Milky Way did not form in isolation. Instead, they grew to their immense sizes over billions of years by gravitationally cannibalizing smaller satellite galaxies. Andromeda 19 is a pristine example of the kind of building block that would have been consumed in this cosmic feast. Its current state offers us a frozen snapshot of what many other small galaxies likely looked like before they were torn apart and absorbed by their larger host. This process of galactic cannibalism is not a gentle one. As a satellite galaxy like Andromeda 19 orbits its parent, it experiences intense tidal forces. The gravitational pull from Andromeda stretches the satellite, drawing out long streams of stars and dark matter in a process called tidal stripping. In many cases, this leads to the complete dissolution of the satellite, its stars becoming part of Andromeda's extended halo. Andromeda 19 appears to be in an early stage of this process. Its incredibly diffuse nature suggests it has already been significantly stretched and shaped by these tidal forces, its outer layers slowly being peeled away over eons. It is a galaxy in the process of being unmade, its identity gradually dissolving into that of its colossal neighbor. Studying systems like Andromeda 19 allows astronomers to peer back in time and reconstruct the assembly history of the great spiral galaxies we see today. By mapping the positions, motions, and properties of these dark satellites, they can trace the legacy of ancient mergers and accretion events. Each faint, diffuse galaxy is a surviving piece of cosmic archaeology, a relic from an earlier era when the universe was a more violent and chaotic place. They are the lingering evidence of a grand, billion-year construction project, showing us that the majestic Andromeda galaxy we see today is actually a composite, built from the remains of countless smaller ghosts it has consumed throughout its long history. While Andromeda 19 presents a ghostly spectacle, it is far from alone in its obscurity. Another satellite of the Great Spiral, Andromeda 21, reveals an even more extreme and distorted version of this dark tale. Discovered in the same sweep of the sky as its cousin, this dwarf spheroidal galaxy is a masterclass in how pure gravitational dominance can shape a celestial object into a faint, elongated whisper against the backdrop of space. Its story is not just one of darkness but of survival, sculpted by the relentless pull of its giant neighbor and the unseen hand of the matter that holds it all together. To the most powerful telescopes, Andromeda 21 appears as little more than a faint smudge of ancient stars. Its luminosity is staggeringly low, emitting only a tiny fraction of the light of even a small globular cluster. This incredible dimness makes it one of the least luminous galaxies known in the local universe, a true cosmic phantom where the distances between stars are vast and the darkness between them is nearly absolute. But its most striking visual feature is its shape. Unlike the roughly spherical form of many dwarf galaxies, Andromeda 21 is distinctly elongated, stretched out as if caught in a cosmic tug-of-war. This distorted morphology is the first major clue to the intense forces acting upon it. The true nature of this galaxy is revealed not by its light but by the motion of its stars. Detailed kinematic studies, which measure the velocities of these individual suns, paint a picture of astonishing gravitational strength. The stars within Andromeda 21 are moving at speeds that should, by all rights, cause the entire tenuous structure to fly apart. The fact that it remains bound together indicates the presence of a massive, dense halo of dark matter providing the gravitational glue. The calculated mass-to-light ratio for this galaxy is one of the highest ever recorded, meaning that for every single photon of light it emits, there is an unimaginably vast quantity of invisible mass holding it in place. It is a galaxy where the dark matter doesn't just dominate, it utterly overwhelms. This immense dark matter halo is not just a passive anchor, it is the key to the galaxy's very survival. Andromeda 21 orbits perilously close to its gigantic host, well within the zone where tidal forces are incredibly powerful. The gravity of the Andromeda galaxy exerts a tremendous pull on the satellite, trying to rip it apart. The stars and any loose gas in the outer regions of Andromeda 21 are vulnerable to this stripping effect. However, its secret weapon is the deeply concentrated core of its dark matter halo. This dense, invisible nucleus acts as a gravitational shield, fiercely holding onto the galaxy's central regions and allowing it to withstand the tidal onslaught that would have long since destroyed a less massive object. This ongoing gravitational interaction has profoundly shaped the galaxy we see today. Astronomers theorize that the elongated, stretched-out form of Andromeda 21 is a direct result of tidal stripping. As it travels along its orbit, the pull from Andromeda has drawn out its contents, transforming its shape and effectively puffing up its outer layers while the dark matter-rich core remains intact. It exists in a delicate equilibrium, a celestial dance between destruction and preservation. This makes it a living laboratory for studying the resilience of dark matter halos and the processes that govern the evolution of satellite galaxies. Andromeda 21 is more than just a dark galaxy. It is a testament to the invisible architecture of the cosmos, a faint and distorted survivor clinging to existence in the overwhelming shadow of a giant. Now we turn to another enigmatic resident of Andromeda's orbit, a satellite that pushes the limits of what we thought possible for a dwarf galaxy. Meet Andromeda 25, a system so dominated by its unseen mass that it stands as one of the most compelling and challenging dark matter laboratories in the local universe. While its fellow satellites like Andromeda 19 and 21 are certainly ghostly, Andromeda 25 distinguishes itself through an almost unbelievable measurement, its mass-to-light ratio. The sheer amount of dark matter inferred to be packed within this relatively small volume of space is so extreme that it forces cosmologists to re-examine the very simulations used to predict how such structures should form. The initial discovery of Andromeda 25, like many of its cousins, came from large-scale stellar surveys meticulously mapping the environs around the Andromeda galaxy. It was catalogued as a dwarf spheroidal galaxy, a faint, elongated collection of ancient stars, but the true revelation of its nature came from detailed spectroscopic follow-up observations. By carefully measuring the Doppler shifts of light from its individual stars, astronomers could calculate their velocities and thus the gravitational forces at play within the galaxy. The results were staggering. The stars were whipping around at velocities far too high to be explained by the gravitational pull of the visible matter alone. The math was unequivocal. An immense amount of unseen mass was required to hold the galaxy together, resulting in a mass-to-light ratio that ranks among the highest ever recorded for a galaxy of its type. This profound dark matter dominance immediately points to a fascinating and violent history. One leading theory suggests that Andromeda 25 may not be a pristine, undisturbed dwarf galaxy at all. Instead, it could be the surviving core of a much larger system that was torn apart in a dramatic encounter billions of years ago. In this scenario, a more massive progenitor galaxy ventured too close to Andromeda. The immense tidal forces from this interaction would have violently stripped away the outer layers of stars and gas, which were only loosely bound. What remained was the innermost, densest part of the galaxy, a region incredibly rich in dark matter. This process would leave behind a compact, dark matter-dominated fossil, which is exactly what we observe in Andromeda 25. Its elongated shape further supports this idea, as it's consistent with the stretching and distortion caused by tidal forces. However, this very explanation is also the source of a significant challenge for modern cosmology. The standard model of the universe, known as the lambda cold dark matter model, is incredibly successful at predicting the large-scale structure of the cosmos. But when it comes to the small scale specifically, the number and properties of dark matter-rich dwarf galaxies around hosts like Andromeda and the Milky Way, a persistent problem emerges. Our most sophisticated computer simulations consistently predict that large galaxies should be surrounded by many thousands of small, dark matter clumps, the vast majority of which would be too dark to see. Yet, we only observe a few dozen such satellites. This is known as the missing satellites problem. Andromeda 25 deepens this mystery. While its existence confirms that such dark matter-dominated dwarfs are real, its extreme properties are difficult to reconcile with the simulations. The dark matter halos produced in these virtual universes often aren't quite dense or massive enough in their centers to match the intense gravitational pull we measure in objects like Andromeda 25. This discrepancy suggests that there might be a flaw in our understanding of how dark matter behaves on these small scales. Perhaps dark matter has properties we haven't yet accounted for, allowing it to cluster more densely than our models allow. Or the simulations might be missing key physics related to how supernova and stellar feedback can actually push dark matter around, inadvertently making these central cores even denser over time. Andromeda 25, therefore, is more than just another dark galaxy. It is a crucial data point in a grand cosmic debate. Its mere presence confirms the overarching theory that dark matter is the scaffolding of the universe, but its specific, extreme characteristics highlight the gaps in our understanding of the finer details. It serves as a natural experiment, a cosmic outlier whose very existence compels us to refine our models, to look deeper into the physics of the invisible, and to acknowledge that even our most successful theories are still a work in progress, constantly being shaped and challenged by the faint, dark ghosts we discover in the sky. Orbiting our own Milky Way is a ghost of epic proportions, a celestial phantom so vast and yet so faint that it evaded detection until this very century. This is Crater II, a dwarf spheroidal galaxy that holds the paradoxical title of being one of the largest galaxies in the local group, while simultaneously ranking among the dimmest objects ever catalogued in the sky. Its discovery in 2016 was a stunning reminder of how much we have yet to discover in our own cosmic backyard, hidden not in the far reaches of the universe, but right here in the halo of our home galaxy. The sheer scale of Crater II is difficult to overstate. It spans an incredible diameter of approximately 7,000 light-years. To put that into perspective, if you could place it next to our Milky Way, it would appear about 2/3 as wide as our galaxy's brilliant disk. Yet, despite its enormous physical size, its light is spread so incredibly thin that it produces a surface brightness hundreds of times fainter than the natural glow of Earth's own night sky. This is why it remained hidden for so long. Its stars are so few and so widely dispersed that they simply blended into the background of more distant Milky Way stars. It wasn't found by seeing a concentrated smudge of light, but through sophisticated computer algorithms that analyzed data from the VST Atlas survey, identifying a subtle statistical overdensity of stars all moving together through space. This was the signature of Crater II, a colossal ghost revealed by its synchronized motion, not its glow. The paradox of its size and its faintness immediately points to one thing: an overwhelming dominance of dark matter. When astronomers measured the velocities of its stars, they found them moving at speeds that demand a tremendous gravitational anchor. The calculations reveal that Crater II possesses a massive dark matter halo with a total mass nearly 150 million times that of our Sun. However, the amount of mass that actually emits light its stars is almost negligible in comparison. This results in a mass-to-light ratio that is extraordinarily high, meaning that for every bit of light its stars produce, there is an astronomical amount of invisible mass holding everything together. In essence, Crater II is a titanic sphere of dark matter with a few lonely stars sprinkled throughout, like a handful of grains of sand scattered inside a massive, invisible balloon. This leads to the compelling and unanswered question: how did such a giant dark galaxy form? Scientists are actively investigating two primary theories. The first suggests that Crater II may be a primordial failure. It could have collapsed early in the universe's history, gathering an immense halo of dark matter, but for some reason, it never managed to accumulate much gas to form a correspondingly huge population of stars. Perhaps it was born in a barren region of space, or its gas was somehow heated and prevented from cooling and collapsing. The second, and perhaps more dynamic theory, posits that Crater II was not always this dark. It might have once been a more typical dwarf galaxy with a healthier number of stars, but it has been victimized by the immense gravitational forces of the Milky Way. As it travels on its long orbit around our galaxy, it may have passed through the galactic disk multiple times. Each passage would have subjected it to brutal tidal forces, gravitational shocks that can violently strip away a dwarf galaxy's outer stars and gas. This process, repeated over billions of years, could have puffed up the galaxy, stretching it to its enormous size while simultaneously robbing it of its visible matter, leaving behind the dark, expanded phantom we observe today. Crater II stands as a silent monument to the destructive and creative forces of gravity, a giant hiding in plain sight, its true story written in the motion of its stars and the immense invisible weight that binds them. Traveling far beyond the familiar satellites of our local group, we venture into the deep southern sky to meet an ancient cosmic fossil, a galactic witness to the universe's first dawn. This is Tucana II, a dwarf galaxy so old and pristine that it serves as a direct portal back to a time when the first structures were only just beginning to coalesce from the primordial darkness. Unlike the ghostly, stretched giants we've encountered, Tucana II is a compact and incredibly faint system, but its true significance lies not in its size, but in its profound age and the secrets it holds about the distribution of the universe's hidden mass. Tucana II is classified as an ultra-faint dwarf galaxy, and it orbits our own Milky Way at a great distance. What immediately sets it apart from most other galaxies is its extreme metal poorness. In astronomy, metals refer to any element heavier than hydrogen or helium. These elements are forged in the nuclear furnaces of stars and scattered across the cosmos when those stars die in supernova explosions. The fact that the stars in Tucana II contain almost none of these heavier elements means they are among the first generation of stars ever to form. They are made almost exclusively from the pristine hydrogen and helium that emerged from the Big Bang, making this galaxy a living relic, a preserved piece of the early universe that has evolved little in over 13 billion years. Studying it is like opening a time capsule from the cosmic dark ages. For a long time, astronomers understood Tucana II to be a typical, if ancient, dwarf galaxy with a tight core of stars. But a recent discovery using the SkyMapper telescope in Australia and the Magellan telescopes in Chile completely upended that simple picture. Researchers mapped the positions of stars belonging to Tucana II and made an astonishing find. A population of its distinctive, metal-poor stars were not in the main body of the galaxy at all. Instead, they were scattered incredibly far from the center, extending the galaxy's known reach by a factor of 3 or more. These stars were located thousands of light years away from the core, yet their chemical signature and motion proved they were gravitationally bound to Tucana II. This was a puzzle. Stars that distant should have long ago been stripped away by the tidal forces of the Milky Way, unless something incredibly powerful was holding them in place. The only force strong enough to explain this vast stellar halo is an immense and extended distribution of dark matter. The presence of these distant stars acts as a gravitational tracer, allowing scientists to map the unseen mass that must be there. The calculations revealed that Tucana II's dark matter halo is far larger and more massive than anyone had previously imagined for a galaxy of its tiny stellar size. To hold onto stars so far out, its dark matter halo must be both enormous and surprisingly resilient. This finding was a major revelation, suggesting that the very first galaxies in the universe were not the small, compact objects we once thought. Instead, they were likely already bedecked with extensive, massive halos of dark matter from their very inception, providing a gravitational well deep enough to capture gas and begin forming those first precious stars. This extended dark matter halo makes Tucana II a cornerstone object for understanding galaxy formation. It provides some of the strongest evidence yet that the first mini-galaxies were incredibly dark matter dominated from the very beginning. Their visible stars were just a tiny, luminous flag planted in the center of a vast, invisible mountain of mass. This has profound implications for how we model the evolution of the universe. It suggests that dark matter clumped together earlier and more effectively than some simulations predicted, creating gravitational anchors that allowed the first stellar seeds to take root quickly after the Big Bang. Tucana II, in its ancient, silent orbit, is telling us that the dark matter scaffolding for all future structure was already firmly in place when the universe was still in its infancy, setting the stage for everything that was to come. While many of the dark galaxies we've explored orbit closer to their hosts, our next subject is a lonely wanderer, adrift in the cosmic ocean between the great galactic clusters. This is Horologium I, an ultra-faint dwarf galaxy discovered in 2015 as a subtle statistical ghost within the vast datasets of the Dark Energy Survey. Its identification was a triumph of modern data mining, a faint smudge of ancient stars pulled from the noise by algorithms designed to see what the human eye could not. Isolated and incredibly distant, Horologium I might seem insignificant at first glance, but its quiet existence tells a story of immense gravitational power and provides a critical test for our most fundamental theories of the cosmos. Nestled in the southern constellation of the Clock, Horologium I is one of the most remote satellite galaxies known to be associated with the Milky Way, lying over 200,000 light-years from Earth. Its extreme faintness means it contains only a few thousand ancient stars, all composed of the primordial hydrogen and helium forged in the Big Bang. This lack of heavier elements confirms its status as a pristine fossil. A galaxy that effectively shut down its star formation processes billions of years ago, preserving a snapshot of the universe's earliest epochs. Its stars are so sparse that if you were standing on a planet within it, the night sky would be nearly empty, a profound and absolute darkness punctuated by only a few distant, lonely suns. The true revelation of Horologium I's nature came not from imaging its faint light, but from measuring the motion of its stars. Using the world's most powerful telescopes, like the Very Large Telescope in Chile, astronomers performed detailed spectroscopic observations to precisely calculate the velocities of its individual stars. The results were startling. Despite the galaxy's tiny stellar population, its stars were moving at remarkably high speeds. This frantic motion is the unmistakable signature of a deep gravitational potential well. The only force powerful enough to prevent these fast-moving stars from instantly flying off into the void is the immense gravitational pull of a massive, concentrated halo of dark matter. Calculating the mass required to bind these stars yields a truly astonishing number. Horologium I possesses a mass-to-light ratio that is among the highest ever measured. This means that for every single photon of light its ancient stars produce, there is a staggering amount of invisible mass, orders of magnitude more dark matter than normal matter. It is, for all intents and purposes, a massive, dense knot of dark matter that has managed to capture and hold onto a tiny, insignificant sprinkling of stars. This extreme discrepancy makes it one of the most dark matter-dominated objects ever discovered in the universe. This extreme characteristic is what elevates Horologium I from a mere curiosity to a cornerstone of cosmological theory. Its existence and properties provide a powerful and direct test for the lambda-cold dark matter model, which is the prevailing standard model of the universe. This model predicts that the cosmic web is built from the bottom up, with small clumps of dark matter forming first and later merging to build larger galaxies. According to the simulations, vast numbers of these small, pristine dark matter clumps, known as low-mass halos, should be orbiting within the halo of every large galaxy like our Milky Way. For a long time, a major problem plagued this theory, the so-called too big to fail problem. The most sophisticated computer simulations predicted that the most massive of these dark matter subhalos should be so dense that they would have easily formed stars and should now be observed as bright, large dwarf galaxies. Yet, when we looked at the sky, we didn't see them. These massive subhalos appeared to have failed to form the bright galaxies the simulations said they should have. Horologium I, along with other ultra-faint dwarfs, is a key piece of the solution to this puzzle. Its discovery shows that these massive dark matter halos do indeed exist, but they are not failing. They are simply incredibly inefficient at forming stars. They are the dark galaxies we've been searching for. Horologium I is a perfect example of one of these predicted primordial dark matter clumps. Its high dark matter density and minimal stellar content align beautifully with the refined predictions of the lambda-cold dark matter model, offering strong supporting evidence that our understanding of the universe's invisible scaffolding is fundamentally correct. It acts as a natural laboratory, allowing us to study the properties of dark matter in its purest, most isolated form, far from the complicating effects of complex star formation and galactic interactions. In its profound silence and isolation, Horologium I speaks volumes, confirming the deep, dark underpinnings of the cosmic order. Now we journey far beyond the halo of the Milky Way to one of its most distant and enigmatic satellites, a cosmic fossil adrift in the constellation of Eridanus. This is Eridanus II, an ancient dwarf galaxy whose quiet, unassuming appearance conceals a gravitational secret so profound it challenges our understanding of how the universe builds its smallest structures. Discovered in 2015 in data from the Dark Energy Survey, this ultra-faint dwarf galaxy is a relic of the primordial universe, but it holds a monstrous surprise at its heart. A gravitational anchor so dense and powerful that its very existence seems to defy the rules of cosmic formation. Eridanus II is the definition of a fossil galaxy. It is incredibly remote, lying over 1,300,000 light-years from Earth, far beyond the main gravitational influence of the Milky Way. Its stars are few and ancient, composed almost entirely of hydrogen and helium, with a near-total absence of the heavier elements that signal ongoing star formation. This tells us that Eridanus II effectively died billions of years ago. Its star-forming engines shut down, leaving it a silent, static relic of the universe's first chapter. It is a time capsule, a window into an era when galaxies were just beginning to coalesce from the dark. Despite its faintness, its stars are spread across a significant volume, and their motions reveal the now familiar signature of a massive, dominating dark matter halo, binding the entire structure together against the pull of the cosmos. But the true shock within Eridanus II was revealed when astronomers trained the powerful eyes of the Magellan telescopes and the very large array on its core. Nestled at the very center of this diminutive, faint galaxy, they found evidence of a gravitational monster, a candidate for an intermediate mass black hole. This is not the supermassive black hole that resides at the heart of our Milky Way, weighing millions of solar masses, nor is it a stellar mass black hole from a collapsed star. This object is estimated to be roughly 20,000 times the mass of our Sun, placing it in a rare and elusive category that has been incredibly difficult to find. The evidence came from a compact, bright source of radio waves emanating from the exact galactic center, a signature often associated with the violent accretion disks surrounding black holes. The presence of such a massive black hole in such a small, ancient galaxy is a paradox that strikes at the heart of galactic evolution. How did it get there? Our standard models suggest that supermassive black holes grow over time through mergers and by accretion of gas, processes that occur in large, dynamic galaxies. A tiny, dormant fossil like Eridanus II should not have had the raw materials or the turbulent history to build and feed such a dense object. This forces scientists to consider two radically different origin stories, each with profound implications. The first theory is that this black hole is a primordial seed, a direct collapse black hole that formed in the very earliest moments of the universe. In this scenario, a massive cloud of pristine gas could have collapsed under its own weight, bypassing star formation entirely and directly forming a black hole. This primordial seed would then have been present from the very birth of Eridanus II, acting as a gravitational nucleus around which the first stars and the dark matter halo assembled. If true, this would mean that some of the very first galaxies were built around these ancient black holes, a concept that would completely reshape our narrative of cosmic dawn. The second, more dynamic theory suggests the black hole is not a native-born object but an immigrant, acquired through a violent act of galactic cannibalism. Billions of years ago, Eridanus II might have been a larger, more substantial dwarf galaxy that devoured an even smaller neighbor. If that consumed galaxy itself contained a central black hole, the merger could have deposited the black hole at the core of Eridanus II, where it settled and has remained ever since. This would mean that even the smallest, faintest galaxies in the universe have a hidden history of violence and merger, a complexity we are only just beginning to appreciate. Beyond its origin, the black hole in Eridanus II ignites a deeper, more speculative question about the nature of dark matter itself. Could there be a connection between this visible point of immense gravity and the invisible dark matter halo that surrounds it? Some theorists propose that dense objects like black holes could act as nucleation sites, attracting and concentrating dark matter particles around them. If certain types of dark matter particles can interact with each other and annihilate upon collision, the region around a black hole could be a focal point for this process, potentially producing detectable signals. Eridanus II, with its combination of a massive dark matter halo and a central black hole, becomes a unique natural laboratory to search for such interactions, potentially offering a new pathway to finally detecting dark matter. Eridanus II is far more than a simple dark galaxy. It is a cosmic Russian doll presenting mystery within mystery. Its existence suggests that the ancient universe was a place of unexpected complexity, where even the smallest galaxies could forge gravitational giants. It challenges the simple idea that a galaxy's size dictates its potential for hosting massive central objects. This faint smudge of ancient stars, a relic from the dawn of time, forces us to reconsider the fundamental pathways of galaxy formation and asks us to ponder the possible and deeply mysterious links between the black holes we can see and the dark matter we cannot. Our journey now takes us to a strange and enigmatic object that blurs the very line between a star cluster and a galaxy, a celestial Rorschach test that has divided astronomers and forced us to question our most basic definitions. This is Willman 1, a faint smudge of light discovered by astronomer Beth Willman in 2004 within data from the Sloan Digital Sky Survey. For nearly 2 decades, it has occupied a controversial and uncomfortable space in our catalogues, stubbornly refusing to be neatly categorized. It is a cosmic chimera, possessing qualities of both a globular cluster and a dwarf galaxy, and its true identity hinges entirely on the immense, unseen mass that appears to be holding it together. At first glance, Willman 1 looks incredibly unimpressive. It is a sparse collection of only a few hundred stars, so faint that its total luminosity is less than 1,000 times that of our Sun. To put that into perspective, a single bright giant star could outshine this entire object. Its physical size is also minuscule, spanning only about 25 light-years across. In many ways, it bears a striking resemblance to a globular cluster, those ancient spherical swarms of stars that orbit the Milky Way like bees around a hive. These clusters are gravitationally bound, but they are not considered galaxies because they lack a key ingredient, a significant dark matter halo. Their gravity is supplied almost entirely by the collective mass of their visible stars. This is where the story of Willman 1 takes a fascinating turn. When astronomers measured the velocities of the stars within Willman 1, they expected to see the relatively slow, sedate motion characteristic of a cluster whose gravity comes from its stellar mass alone. Instead, they found the stars were moving at surprisingly high speeds. This frantic motion indicated that the gravitational force binding these stars was far stronger than the combined pull of all the visible matter could possibly provide. The calculations pointed to an inescapable conclusion. Willman 1 must be embedded within a massive, extended halo of dark matter. This single measurement thrust it into an entirely different category. While star clusters are held together by the gravity of their stars, true galaxies are defined by being anchored within a much larger halo of dark matter. The evidence suggests Willman 1 is doing just that, making it a strong candidate for the title of the least luminous galaxy ever discovered, a barely there wisp of a system that is nonetheless built upon the same dark foundation as cosmic giants. This classification crisis is not unique to Willman 1. It represents a growing challenge in modern astronomy. As our telescopes and detection methods become more sensitive, we are finding a whole menagerie of ultra-faint objects populating the faint end of the galaxy luminosity function. This is the final frontier of galactic discovery, a realm where the traditional lines between different classes of objects become hopelessly blurred. We are now finding systems with so few stars that their properties overlap with those of star clusters. The only reliable way to tell them apart is to probe their dynamics and measure their mass. An object with a high mass-to-light ratio is almost certainly a galaxy, its identity revealed not by its light but by its darkness. Willman 1 is a perfect case study in this new astronomical discipline, forcing us to rely on the motion of stars to understand the invisible architecture that defines a true galaxy. The intense study of objects like Willman 1 is crucial because they are thought to be the leftover building blocks of the universe, the pristine fossils from which larger galaxies like our Milky Way were assembled. The lambda-cold dark matter model predicts that thousands of these dark matter clumps should be orbiting within the halo of every large galaxy. The fact that we see only a few dozen that have managed to form stars creates the famous missing satellites problem. Willman 1 and others like it may represent the visible tip of a vast iceberg. They could be the rare examples where just enough gas was captured to form a handful of stars, allowing us to detect them and study the properties of the countless other, completely dark halos that must be lurking unseen. Each one we find helps us calibrate our models of cosmic structure formation, offering a unique window into the distribution of dark matter on the smallest scales. Whether Willman 1 is ultimately classified as a dwarf galaxy or an unusual star cluster, its value is undeniable. It serves as a critical benchmark, a natural experiment that tests the limits of our definitions and our understanding. It demonstrates that the universe is full of subtle and ambiguous objects that defy our desire for simple categorization. In its faint, ambiguous glow, we are reminded that nature is under no obligation to conform to our textbooks, and that some of the most profound discoveries lie in the gray areas, in the quiet, dark margins of the cosmos where the rules are still being written. Hiding within the starry hair of the constellation Coma Berenices lies a cosmic paradox, a faint whisper of a galaxy that holds one of the most profound gravitational secrets in the universe. This is the Coma Berenices dwarf galaxy, an unassuming ultra-faint satellite of the Milky Way that was first pinpointed in 2006 as a subtle, barely there smudge in the data of the Sloan Digital Sky Survey. To the most powerful telescopes, it appears as nothing more than a sparse sprinkling of ancient stars, a celestial ghost so faint that its light is easily lost in the background glow of the night sky. Yet, this apparent insignificance is a masterful illusion, a cosmic sleight of hand that conceals a density of dark matter so extreme it pushes the very limits of what we thought was physically possible. The true nature of this ghost was revealed through the precise science of dynamical mass measurement. Astronomers used the world's largest telescopes to perform a delicate astronomical ballet, carefully measuring the subtle wobbles and Doppler shifts in the light from its individual stars. By tracking their velocities, they could map the gravitational field holding the galaxy together. The results were nothing short of staggering. The handful of stars in Coma Berenices are whipping around at velocities that should instantly tear the entire structure apart. The only possible explanation is that an immense, unseen mass is providing a gravitational anchor of unbelievable strength. When the calculations were complete, they yielded a mass-to-light ratio that is among the highest ever recorded. For every single bit of light emitted by its stars, there is well over 1,000 times more mass in the form of completely invisible dark matter. This galaxy is not just dominated by dark matter, it is utterly overwhelmed by it, a place where the invisible cosmic scaffolding doesn't just support the structure, it is the structure with the stars serving as mere accidental decorations. This incredible density of dark matter packed into such a small volume makes Coma Berenices far more than just another cosmic curiosity. It transforms it into a crucial natural laboratory for probing the fundamental nature of dark matter particles themselves. The prevailing theory, known as the cold dark matter model, assumes that dark matter particles are cold, meaning they move slowly and can clump together very effectively into dense cores. The existence of ultra-dense halos like the one in Coma Berenices supports this general picture. However, the extreme density we observe here also allows scientists to test more specific properties. For instance, it helps place constraints on how much dark matter particles might interact with each other or with normal matter. If dark matter had any significant interacting or collisional properties, it would smooth out these ultra-dense peaks, preventing them from forming. The fact that such a dense core exists suggests dark matter is exceptionally non-collisional, meaning particles can pass right through each other without effect. Furthermore, the sheer density of the halo makes Coma Berenices a prime target in the search for indirect signals of dark matter annihilation. One of the leading candidates for dark matter is a theoretical particle known as a WIMP, or weakly interacting massive particle. A key property of some WIMP is that they can be their own antimatter counterparts. When two of them collide, they could annihilate each other in a flash of energy, producing secondary particles like gamma rays. The probability of this happening is directly related to the square of the density of dark matter particles. In a place like the core of the Coma Berenices dwarf, where the dark matter is packed so densely, the chances of such collisions and annihilations would be dramatically higher. Astronomers are therefore intensely scanning this faint galaxy with gamma-ray telescopes, hoping to catch a glimpse of this telltale energy signature. A detection here would not only confirm the existence of dark matter particles, but could also reveal their mass and cross-section, finally cracking a mystery that has persisted for decades. This tiny, faint smudge in the sky has become a beacon, its profound darkness potentially holding the key to illuminating the true nature of the universe's most abundant yet elusive substance. Drifting through the vast celestial expanse, the Hercules dwarf galaxy presents a stark portrait of gravitational endurance. This ultra-faint satellite of the Milky Way, discovered in 2006, is not a pristine sphere but a profoundly distorted stream of stars, stretched into a long, thin ellipse that betrays a history of immense cosmic violence. Its very shape is a testament to a brutal and ongoing struggle with the overwhelming gravity of our galaxy, a battle that has left it visibly scarred yet remarkably intact. Hercules serves as a perfect natural experiment, demonstrating with stunning clarity the contrasting fates of normal matter and dark matter when subjected to the most extreme forces in the universe. The elongated, almost cigar-like form of Hercules is the direct and inevitable result of tidal forces. As this small galaxy travels along its eccentric orbit, it repeatedly ventures close to the immense gravitational well of the Milky Way. During these close passes, the pull from our galaxy is not uniform. The side of Hercules closer to us feels a stronger tug than the side farther away. This difference in force, the tidal effect, stretches the galaxy, pulling it apart like cosmic taffy. Over billions of years, this process has drawn out its stars into the long, delicate structure we observe today. Normally, this would be a death sentence. Any similarly sized cluster of stars held together only by their own gravity would have been completely shredded and dissolved into the Milky Way's halo eons ago. The fact that Hercules still exists as a coherent, bound structure is the first major clue that something powerful and unseen is holding it together. That something is a massive and resilient halo of dark matter. By measuring the velocities of its stars, astronomers have calculated the gravitational force required to keep them from flying off into the void. The result points to a dark matter content that is staggering in its scale. Estimates suggest Hercules has a mass-to-light ratio in the hundreds, meaning for every bit of light its stars produce, there is several hundred times more mass in invisible form. This dark matter forms a deep gravitational potential well, an invisible anchor that the tidal forces of the Milky Way struggle to break. While the galaxy's visible stars and any loose gas are vulnerable to being stripped away and stretched out, the dark matter halo, which does not interact with itself or other matter, remains largely cohesive. It acts as a protective shield, maintaining the galaxy's core integrity even as its outer layers are relentlessly pulled upon. This dynamic offers a profound lesson in resilience. The Hercules dwarf illustrates a critical distinction in how different types of matter behave under pressure. The normal atomic matter, the stars and gas, is directly affected by the tidal forces and can be stripped away. The dark matter, however, feels only gravity and is thus far more robust against this kind of disruption. Its halo may be slightly distorted by the interaction, but it retains its essential mass and gravitational dominance, ensuring the galaxy's survival. This makes Hercules a powerful demonstration of the foundational role dark matter plays in the longevity of galactic structures, especially those dwelling in the punishing environment of a massive host's gravitational field. Studying systems like Hercules allows cosmologists to refine their models of dark matter itself. The fact that its halo has withstood such intense tidal stripping suggests certain properties about the particles that constitute it. Specifically, it supports the idea that dark matter is cold, meaning its particles move relatively slowly, allowing them to clump together effectively into stable, dense halos. It also suggests the particles are effectively collisionless. If they interacted with each other frequently, the tidal forces would have likely caused the halo to evaporate or dissipate over time. In its silent, stretched-out struggle, the Hercules dwarf galaxy is not just a victim of gravity. It is a key witness, providing vital evidence for the very nature of the dark, invisible substance that shapes our universe. Lurking in the constellation of Leo, another ghostly satellite adds its silent testimony to the dark matter map enveloping our galaxy. This is Leo IV, an ultra-faint dwarf discovered in 2006, a celestial fossil whose sparse collection of ancient stars tells a story of profound isolation and gravitational dominance. Its incredible remoteness, lying over 500,000 light-years from Earth, places it far out in the Milky Way's extended halo, a lonely sentinel on the very frontier of our galaxy's gravitational influence. This isolation is key to its story, as it has likely spent almost its entire existence in the deep freeze of intergalactic space, far from the disruptive forces that have shaped satellites closer in. The appearance of Leo IV is one of extreme fragility. It contains only a few thousand stars, all of them ancient and metal-poor, indicating that its star formation ceased billions of years ago. These stars are not clustered in a tight ball, but are instead scattered across a significant volume, giving the galaxy an exceptionally low surface brightness. If you were to somehow view it from within, the sky would be a near-perfect blackness, with a few faint suns spread so far apart that each would appear utterly alone in the void. This tenuous structure makes it incredibly vulnerable, and yet it has persisted for eons. The fact that it hasn't simply dissipated into the halo of the Milky Way is the first major clue that an unseen force is binding it together. That force, of course, is dark matter. The pivotal evidence comes from studying the motion of its stars, a technique known as measuring velocity dispersion. Astronomers use the world's most powerful telescopes to take precise spectra of individual stars within Leo IV. By analyzing the subtle Doppler shifts in their light, they can calculate how fast each star is moving relative to the others. In a system held together only by the gravity of its visible stars, these motions would be relatively slow and sedate. But the data from Leo IV reveals something entirely different. Its stars are zipping around at surprisingly high velocities, their frantic dance indicative of a deep and powerful gravitational well. The math behind this is both elegant and revealing. The spread of these velocities, the dispersion, is directly related to the total mass contained within the galaxy's orbit. The greater the velocity dispersion, the more mass is required to provide the gravitational pull to prevent the stars from escaping. For Leo IV, the calculated mass is enormous, resulting in a mass-to-light ratio that is phenomenally high. This confirms that, like its ultra-faint cousins, Leo IV is utterly dominated by a massive, extended halo of dark matter. Its visible stars are merely trace markers, insignificant tracers outlining the presence of a vast, invisible mountain of mass. Beyond its role as another dark matter anchor, Leo IV may also hold clues to a more dynamic past. Some studies of its stellar population suggest it might not be a single, pristine structure. There are tantalizing hints in the data that its stars might not all share a uniform velocity or chemical composition. This opens up the possibility that Leo IV could itself be the product of a much older, more ancient merger. Perhaps the remnants of two even smaller protogalaxies that collided and merged in the distant past, their combined dark matter halos creating the stable structure we see today. If confirmed, this would add a layer of cosmic violence to its history, showing that even the quietest, most isolated ghosts can have a dramatic origin story. By pinpointing galaxies like Leo IV and precisely measuring their dynamics, astronomers are slowly but surely building a three-dimensional map of dark matter distribution throughout the Milky Way's halo. Each of these faint dwarfs acts as a gravitational probe, its stars tracing the contours of the invisible mass that holds it. The precise positions and properties of these dark matter satellites provide critical data to test the lambda cold dark matter model on the smallest scales, helping to solve puzzles like the missing satellites problem. Leo IV, in its silent, distant orbit, is not just a passive relic. It is an active data point in our grand quest to understand the hidden architecture of our cosmic home. But the story of Leo IV is not a solitary one, for its celestial neighbor, Leo V, tells a tale so intertwined it suggests a grander, more unified history written in darkness. Discovered just a year after its apparent sibling, Leo V shares a remarkable number of characteristics. It too is an ultra-faint dwarf, a sparse collection of ancient stars residing at a similar, vast distance from the Milky Way center. Their proximity in the sky is not mere coincidence. Their three-dimensional positions and their measured velocities through space reveal an astonishing connection. These two ghostly galaxies are not just neighbors, they are likely siblings, two remnants that may have once been part of a single, larger system, or are now gravitationally dancing together as part of a larger, invisible cosmic stream. This intimate link transforms them from individual curiosities into a paired laboratory, offering a unique opportunity for astronomers. By studying the two galaxies in tandem, scientists can perform a kind of cosmic triangulation, mapping the gravitational field between them. The motions of each galaxy are influenced not only by the pull of the entire Milky Way's dark matter halo, but also by their mutual gravitational attraction to each other. This allows researchers to probe the distribution of dark matter on an intermediate scale, between the confines of a single dwarf galaxy and the entirety of the galactic halo. The precise details of their orbital dance can reveal the density and clumpiness of the dark matter that permeates the space around them, providing a crucial test for simulations that predict how dark matter should be distributed. The existence of this potential pair deepens the mystery of the Milky Way's assembly. One compelling theory suggests that Leo IV and Leo V are not independent galaxies at all, but the two largest and brightest surviving knots of stars within a much larger, invisible structure, a dark matter subhalo stream. In this scenario, a more substantial dwarf galaxy was captured by the Milky Way billions of years ago. Over countless orbits, the immense tidal forces of our galaxy have stretched and shredded it, pulling the majority of its stars into a vast, faint river that flows through the halo, a stream so diffuse its starlight is lost in the background. Leo IV and Leo V would be the surviving cores of that progenitor, the densest clumps of dark matter that managed to retain their tiny stellar populations while the rest of the galaxy was dissolved into nothingness. This idea of a shared origin is bolstered by studies of their stellar populations. Both galaxies show signs of complex star formation histories, with subtle variations in the metallicity and ages of their stars. This could be the chemical fingerprint of that ancient disruption event, a record of the internal dynamics of the original galaxy before it was torn asunder. If proven, this would mean we are not looking at two separate galaxies, but at the scattered bones of a single, devoured system, its story etched into the motions and compositions of its surviving stars. Ultimately, the Leo pair acts as a powerful lens, focusing our view on the hidden substructure of our galaxy's halo. Their combined properties challenge us to see beyond the visible and to map the intricate web of dark matter filaments and subhalos that theory predicts should be there. They are a reminder that the majestic spiral of the Milky Way we see is merely the brightest part of a far more massive and complex dark matter ecosystem, a system built from the remnants of countless cannibalized dwarfs whose ghosts, like Leo IV and Leo V, continue to orbit in silent testament to a violent and dramatic past. Moving from the interconnected ghosts of Leo, we now turn to one of the first and most pivotal ultra-faint dwarfs ever discovered, an object that helped open our eyes to the hidden, dark architecture of our galactic neighborhood. This is Boots 1, a faint smudge of light in the constellation of the Herdsman, whose unassuming appearance belies its monumental role in rewriting our understanding of the cosmos. Its discovery in 2006 was a watershed moment, a clear signal that the Milky Way's halo was teeming with previously invisible, dark matter-dominated fossils, each one a critical piece of the puzzle in our quest to understand the universe's hidden mass. Boots 1 was one of the original trailblazers found in the pioneering data of the Sloan Digital Sky Survey. To the telescopes that first spotted it, it appeared as nothing more than a subtle overdensity of a few dozen ancient stars, a ghostly patch so faint it was nearly indistinguishable from the background. Its total luminosity is less than 100,000 times that of our Sun, meaning it contains only a minuscule fraction of the stars found in even a small globular cluster. This incredible dimness is a hallmark of its type, but it was the subsequent investigation into its dynamics that revealed its true, astonishing nature and cemented its importance in the annals of astronomy. The real story of Boots 1 unfolded when astronomers turned their most powerful spectroscopic instruments toward it. By carefully analyzing the light from its individual stars, they could measure their radial velocities, the speed at which they are moving towards or away from us. The results were stunning. Despite the galaxy's tiny stellar population, the stars were whipping around at velocities far too high to be explained by the gravitational pull of their own visible mass. The spread of these velocities, known as the velocity dispersion, was enormous. This frantic stellar motion pointed unequivocally to a deep gravitational potential well, one that could only be supplied by a massive, dominating halo of dark matter. When the calculations were complete, the numbers were staggering. Boots 1 was found to have a mass-to-light ratio of around 100 to 1. This means that for every single unit of light its stars produce, there is roughly 100 times more mass present in an invisible form. In practical terms, this translates to a total mass of over 1 million solar masses, all bound up in a dark matter halo that is hundreds of times more massive than the combined weight of every single visible star in the galaxy. This extreme measurement instantly transformed Boots 1 from a faint curiosity into an archetype of the dark galaxy, a place where the invisible scaffolding of the universe is not just present but is overwhelmingly the defining characteristic. This profound dark matter dominance is what makes Boots 1 such a crucial object for testing the lambda-cold dark matter model, which is the prevailing theoretical framework for our universe. This model makes a very specific prediction that the halos of large galaxies like our Milky Way should be filled with thousands of smaller dark matter clumps known as subhalos. These subhalos are the leftover building blocks from which the galaxy was assembled, the pristine fossils of the early universe. According to the simulations, many of these subhalos should be massive enough to have attracted gas and formed stars, becoming the dwarf galaxies we see today. For a long time, there was a major problem. The number of observed dwarf satellites around the Milky Way was orders of magnitude smaller than the number of predicted dark matter subhalos. This was the famous missing satellites problem. The discovery of Boots 1 and other ultra-faint dwarfs was a monumental step toward solving it. These galaxies are not missing, they have been here all along. They were simply too faint for us to see. Boots 1 is a perfect example of one of those predicted massive subhalos. It has the high dark matter content the model expects, but it formed stars with incredible inefficiency, resulting in the ultra-faint, ghostly object we detect. Its existence provides powerful supporting evidence that the lambda-cold dark matter model is fundamentally correct on large scales. We just needed the technological capability to find the darkest, most elusive members of the cosmic family. Furthermore, the specific properties of Boots 1's dark matter halo help physicists place constraints on the nature of dark matter particles themselves. The fact that the dark matter is so densely concentrated in such a small galaxy suggests the particles are cold, meaning they move slowly, allowing them to clump together effectively on small scales. If dark matter were warm or faster moving, it would have prevented the formation of such dense cores, smoothing out the distribution of matter. The very existence of Boots 1, with its tightly bound dark matter halo, helps rule out certain models of warm dark matter, narrowing down the possible candidates for what makes up this mysterious substance. In its profound silence, Boots 1 speaks volumes, its darkness illuminating the path toward a deeper understanding of the cosmos. Yet the intrigue of Boots 2 extends far beyond its own faint presence, hinting at a deeper cosmic relationship that could mirror the universe's largest structures on the smallest of scales. Its celestial position and motion through space raise a fascinating possibility. Boots 2 might not be a direct satellite of the Milky Way at all, but rather a satellite of a satellite, a moon of a ghost orbiting its brighter sibling, Boots 1. This concept, known as hierarchical structure, is a cornerstone of the lambda cold dark matter model, predicting that large dark matter halos should themselves contain smaller subhalos, a cosmic nesting of invisible structure. Observational evidence for such a pairing is incredibly difficult to gather given their extreme faintness, but if confirmed, this relationship would be a miniature masterpiece of cosmic architecture. It would demonstrate that the same process that builds galaxy clusters from individual galaxies also operates on the tiniest scales, with dark matter subhalos organizing themselves into their own intricate systems, complete with their own gravitational dependencies. This would provide a stunning validation of our models, showing that the principles of structure formation are universal, repeating from the largest galaxy clusters down to the faintest, most dark matter-dominated dwarfs. Boots 2, in its profound obscurity, offers a unique and powerful test of this fundamental idea, a chance to see the universe's hidden blueprint written in the motion of a few dozen ancient stars. But our exploration of the Boots constellation reveals an even more elusive and enigmatic structure, one that pushes the boundaries of what we can even classify as a galaxy. This is Boots 3, a vast and sprawling celestial ghost that appears less as a coherent object and more as a faint, shimmering river of stars arcing across the sky. Unlike its more compact, albeit faint, neighbors, Boots 3 presents itself as a massive stellar overdensity with a distinctly stream-like appearance, leading many astronomers to conclude they are witnessing the final act of a cosmic tragedy, the ongoing disintegration of a dwarf galaxy as it is consumed by the Milky Way. The very form of Boots 3 tells a story of immense gravitational violence. It does not appear as a rounded blob or a concentrated kernel of stars. Instead, it manifests as a long, thin, and incredibly diffuse ribbon of ancient suns. This elongated, filamentary structure is the classic signature of tidal disruption. For billions of years, this once intact dwarf galaxy has been tracing a long, looping orbit around our Milky Way. With each perilous close pass, the immense and uneven gravitational pull of our galaxy has acted like a cosmic hand, grabbing hold of the dwarf and stretching it. This process pulls stars away from the main body, drawing them out into long leading and trailing arms that trace the galaxy's orbital path. What we call Boots 3 is likely the most prominent surviving clump within this stellar stream, the densest knot of a system that is being systematically unmade before our eyes. The existence and coherence of this vast stream, despite the incredible disruptive forces acting upon it, point unequivocally to the presence of a powerful, unseen anchor. The stars within the stream are all moving together on a similar trajectory, a synchronized flow that requires a tremendous amount of mass to have shaped and maintained it. This is where dark matter enters the narrative once more. Astronomers theorize that the original dwarf galaxy that gave birth to the Boots 3 stream was, like all galaxies, embedded within its own massive halo of dark matter. This invisible halo provided the deep gravitational potential that initially gathered the gas and stars together and now continues to govern the dynamics of the entire stream. Even as the visible stars are being stripped away and scattered, the dark matter halo, which feels only gravity and not tidal friction, continues to guide the motion of the entire structure, its invisible hand shepherding the stellar remnants along their doomed celestial path. This makes Boots 3 and structures like it absolutely vital to reconstructing the Milky Way's violent history of growth and consumption. Each stellar stream is a fossilized orbit, a frozen record of a past accretion event. By meticulously mapping the precise positions, densities, and velocities of stars within the Boots 3 stream, astronomers can perform a kind of galactic archaeology. They can rewind the clock, running sophisticated computer simulations backwards to determine the original mass, orbit, and time of accretion of the progenitor dwarf galaxy. This allows them to piece together the assembly history of our galaxy's halo, one devoured dwarf at a time. Boots 3 is therefore a chapter in the autobiography of the Milky Way, evidence that our grand spiral galaxy continues to grow and evolve by cannibalizing its smaller neighbors, a process that has been ongoing for billions of years and will continue far into the future. The study of such ghostly remnants also provides a unique method for mapping the otherwise invisible dark matter distribution of our galaxy's halo. The shape and curvature of a tidal stream are exquisitely sensitive to the gravitational landscape it flows through. As the stars of Boots 3 travel through the Milky Way's halo, their path is bent and shaped by the lumps and clumps of dark matter they encounter. Any slight kink, wiggle, or variation in the density of the stream can be interpreted as the signature of an interaction with a subhalo of dark matter. In this way, stellar streams act like cosmic fishing lines, their subtle movements revealing the presence of the dark matter fish swimming in the depths of the galactic halo. By analyzing Boots 3, scientists are not just looking at a remnant of the past, they are using it as a tool to probe the present-day, three-dimensional structure of the dark matter that surrounds us, turning a ghost of a galaxy into a precision instrument for uncovering the universe's deepest secrets. Nestled within the vast celestial sphere, another faint whisper from the Milky Way's entourage challenges our notions of cosmic minimalism. This is Segue II, an ultra-faint dwarf galaxy that proves even the most diminutive structures in the universe can be anchored by a gravitational giant. Discovered in 2007 within the treasure trove of data from the Sloan Digital Sky Survey, it initially appeared as little more than a scant handful of stars, a celestial afterthought so faint it barely registered against the backdrop of the night sky. With a total luminosity of only about 900 times that of our Sun, it contains fewer stars than many globular clusters, presenting itself as a truly minimal galaxy. Yet, as with so many of these cosmic phantoms, its true nature is revealed not by the light it emits, but by the frantic, hidden dance of its few stellar inhabitants. When astronomers turned their most powerful spectroscopic instruments toward Segue II, they were met with a result that defied its tiny appearance. By measuring the subtle Doppler shifts in the light from its individual stars, they could calculate their velocities relative to one another. In a system held together solely by the gravity of its visible stars, this motion would be slow and sedate, but the data told a completely different story. The stars within Segue II are moving at surprisingly high speeds, whipping around in a frantic gravitational dance. This high-velocity dispersion was the key clue, the undeniable signature of a deep and powerful gravitational well. The math was unequivocal. To prevent these swiftly moving stars from instantly flying off into the void, an immense amount of unseen mass had to be present, binding the entire structure together. The calculated mass-to-light ratio for Segue II is nothing short of astounding, placing it among the most extremely dark matter-dominated objects known. For every single bit of light produced by its meager collection of stars, there is well over 1,000 times more mass in an invisible form. This means Segue II is essentially a massive clump of dark matter that, almost as an afterthought, managed to capture and hold onto a tiny sprinkling of stars. Its total dark matter halo is estimated to be over 500,000 times the mass of our Sun, all cocooning a stellar population that is almost insignificantly small by comparison. This incredible discrepancy transforms it from a cosmic curiosity into a fundamental benchmark, pushing the very limits of what we understand about the minimum requirements for a galaxy to exist. This is where Segue II presents one of its most profound puzzles to modern cosmology. Our current models of galaxy formation are built on a foundation of dark matter. According to the prevailing lambda cold dark matter theory, the first structures to form in the universe were small clumps of dark matter known as halos. These halos acted as gravitational seeds, pulling in ordinary gas which then cooled, condensed, and eventually formed the first stars, giving birth to the first galaxies. The simulations predict a veritable ocean of these small dark matter halos orbiting within the halo of a large galaxy like our Milky Way. However, they also predict a certain threshold, a minimum mass that a dark matter halo must have for it to efficiently attract and retain enough gas to form stars. Segue II sits right on this precarious edge, its properties straining the lower limits of this theoretical threshold. Its existence forces astronomers to ask a difficult question: how did such a tiny dark matter halo manage to form any stars at all? One compelling theory suggests that Segue II may not have formed in isolation. It could be the remnant of a much larger and more massive system that was violently stripped of its stars and gas through tidal interactions with the Milky Way. In this scenario, it was not born a minimal galaxy, but was made one through a process of catastrophic disruption. Its current state would then be the surviving, dense core of that larger progenitor, a dark matter-rich fossil that has endured a dramatic history of cosmic violence. Its incredibly low metallicity, meaning its stars contain very few elements heavier than hydrogen and helium, supports this idea, indicating its stars are ancient and that it has not experienced significant star formation for billions of years. Alternatively, Segue II might represent a genuine example of a dark matter halo that just barely met the conditions needed to spark star formation. Its struggle to form stars could be a testament to the extreme inefficiency of the process on the smallest scales. Perhaps it only managed to convert a tiny fraction of its available gas into stars before its reservoir was depleted, maybe blown away by the supernova explosions of its first massive stars or stripped away by an early encounter with another object. This would make it a true cosmic underachiever, a dark matter halo that had all the gravitational potential but never quite managed to shine. The intense study of Segue II is far more than an academic exercise. It is a direct probe into the physics of the earliest universe. By identifying the absolute smallest and darkest galaxies, astronomers can place stringent constraints on the nature of dark matter itself. For instance, if dark matter were warm, meaning its particles moved at a significant fraction of the speed of light, it would have difficulty clumping together on such small scales. The fact that a tiny, yet massively dense, object like Segue II exists helps rule out certain warm dark matter models, favoring the cold dark matter paradigm where particles move slowly and can clump together effectively to form even the smallest halos. In its profound minimalism, Segue II acts as a crucial natural experiment, its faint starlight illuminating the complex and often counterintuitive rules that govern the birth of galaxies in a dark matter-dominated cosmos. Far out in the galactic hinterlands, drifting in the faint constellation of Pisces, lies another cryptic sentinel of the Milky Way's dark halo. This is Pisces II, an ultra-faint dwarf galaxy so elusive it was only pulled from the shadows in 2010 by the meticulous data analysis of the Sloan Digital Sky Survey. To our most powerful telescopes, it registers as little more than a subtle smudge, a sparse collection of perhaps 1,000 ancient stars whose combined light is less than 5,000 times that of our Sun. If you were to stand on a hypothetical world within it, the night sky would be a terrifying expanse of near-total blackness, the few distant suns offering little comfort against the overwhelming void. Its incredible remoteness, over 400,000 light-years from Earth, places it in a realm of profound isolation, a fossil preserved in the deep freeze of intergalactic space. Yet, this apparent insignificance is a profound illusion. The true nature of Pisces II is revealed not by its pathetic glow, but by the sheer physical space it occupies and the frantic motion of its few stars. Despite its minuscule stellar population, the galaxy is spread across a diameter of nearly 200 light-years. This large size relative to its star count gives it an extremely low surface brightness, the hallmark of an ultra-diffuse object. But this spaciousness is also the first clue to its massive hidden content. Such a large, fluffy structure should be incredibly vulnerable to disruption. The gravitational tides of the Milky Way should have torn it apart eons ago. The fact that it remains a coherent entity demands a powerful, unseen gravitational anchor. That anchor is, of course, a massive halo of dark matter. The conclusive evidence comes from spectroscopy, measuring the velocities of its individual stars. When astronomers trained their instruments on Pisces II, they found its stars were not moving with the slow, sedate pace expected for a simple cluster of stars. Instead, they were whipping around at surprisingly high velocities, their motion indicative of a deep gravitational potential well. The math is inescapable. To bind these swiftly moving stars within such a large volume requires a tremendous amount of mass. The calculated mass-to-light ratio soars into the hundreds, meaning for every bit of light produced, there is several hundred times more mass present in an invisible form. Pisces II is not a collection of stars that happens to have some dark matter. It is a massive clot of dark matter that has, almost as an afterthought, managed to retain a tiny handful of stars. This extreme property elevates Pisces II from a mere curiosity to a critical data point in the grand cosmological experiment. It, along with its many ultra-faint cousins, acts as a natural laboratory for testing the lambda-cold dark matter model, the prevailing theory of the universe. This model predicts that the halos of large galaxies like our Milky Way should be teeming with thousands of small, dark matter clumps, the leftover building blocks from the universe's formation. For a long time, the number of observed satellite galaxies fell far short of these predictions, creating the famous missing satellites problem. The discovery of galaxies like Pisces II is the key to solving it. These aren't missing, they were simply too dark to see until now. Each one we find is a direct detection of one of those predicted dark matter subhalos. However, Pisces II also presents a subtle challenge. Its properties, specifically the density of its dark matter halo, help physicists place constraints on the nature of the dark matter particle itself. The fact that dark matter can clump into such a dense, massive halo surrounding so few stars supports the idea that it is cold, meaning its particles move slowly, allowing them to collapse effectively into these small-scale structures. If dark matter were warm or faster moving, it would have smoothed out these small-scale density fluctuations, preventing the formation of such dense cores in tiny galaxies. The very existence of Pisces II, therefore, helps rule out certain models of warm dark matter, pushing us closer to understanding the fundamental properties of the universe's most elusive substance. In its profound silence and isolation, this faint smudge of light serves as a precise scale, weighing the invisible and helping to measure the very rules of cosmic architecture. In the far southern skies, within the constellation of the Indian, lies one of the most recently unveiled and enigmatic satellites of our Milky Way, Indus I. Discovered in 2015 by the powerful, wide-field gaze of the Dark Energy Survey, this ultra-faint dwarf galaxy is a classic example of how modern astronomy is no longer just about seeing the light, but about mapping the darkness that governs it. Appearing as little more than a faint statistical whisper against the backdrop of countless more distant stars, Indus I is a ghost of a system containing only a few hundred ancient suns. Its total luminosity is a mere fraction of even a single bright star in our own neighborhood, and if you were to find yourself within its borders, the night sky would be an almost perfect void, a profound and absolute blackness punctuated by only the faintest, most distant points of light. This incredible dimness is precisely why it remained hidden for so long, a secret held by the cosmos until sophisticated computer algorithms could tease its subtle signal from the vast datasets of a digital sky survey. The true revelation of Indus I's nature, like so many of its kind, was uncovered not by its pathetic glow, but by the motion of its stars. When astronomers performed follow-up spectroscopic observations, they measured the velocities of its individual stellar members. The results were unequivocal. Despite the galaxy's minuscule size and tiny stellar population, its stars are moving at remarkably high speeds. This frantic, high-velocity dispersion is the unmistakable fingerprint of a deep and powerful gravitational well. The only force capable of preventing these swiftly moving stars from instantly flying off into the intergalactic void is the immense gravitational pull of a massive, unseen mass. Calculations place its mass-to-light ratio among the highest known, confirming that Indus I is utterly dominated by a vast halo of dark matter. Its visible stars are merely trace particles, insignificant markers outlining the presence of a tremendous, invisible mountain of mass that completely defines the galaxy's existence. The specific celestial address of Indus I is not a trivial detail. It is a critical piece of data in a much larger cosmic cartography project. Its position in the sky, far from the crowded plain of the Milky Way, places it in a relatively clean region for observation, allowing for precise measurements. But more importantly, its location and motion help astronomers map the three-dimensional distribution of dark matter throughout our galaxy's extended halo. Each one of these ultra-faint dwarfs acts as a natural gravitational probe. By pinpointing their exact positions and meticulously tracking their movements, scientists can trace the contours of the invisible dark matter scaffolding that holds them in orbit. Indus I is a single data point, but when combined with the data from dozens of other similar ghosts, it helps to build a detailed mass model of the entire Milky Way system, revealing how much dark matter is present and how it is distributed from the core out to the very farthest edges. This mapping effort is vital for solving one of cosmology's most persistent puzzles, the missing satellites problem. Our prevailing lambda-cold dark matter model predicts that the halo of a galaxy like our own should be swarming with thousands of small dark matter clumps, the leftover building blocks from the universe's formation. For decades, the number of observed satellite galaxies fell dramatically short of this prediction. The discovery of ultra-faint dwarfs like Indus I is the key to resolving this discrepancy. These are the missing satellites. They were never truly missing. They were simply too dark to see until now. Each one, including Indus I, is a direct detection of one of those predicted primordial dark matter subhalos. Its existence and its extreme dark matter content provides powerful supporting evidence that our fundamental model of the universe is correct. It shows us that the dark matter is indeed cold and clumpy, just as the theory predicts, and that it structured itself into these small, dense halos that now orbit our galaxy, most of them so dark they remain entirely unseen, with Indus I being one of the rare few that managed to light a handful of stars, allowing us to find it and confirm the invisible architecture of our cosmic home. From the colossal, silent giant crater II lurking in our own halo to the ancient, black hole-holding fossil of Eridanus II, each of these 25 dark galaxies is a unique and profound mystery. They are not merely celestial oddities, they are fundamental challenges to our understanding of reality itself. These cosmic phantoms force us to confront the unsettling truth that most of the matter in the universe is not just hidden, but is something entirely alien to our experience, a substance that shapes the fate of galaxies without ever revealing its face. They defy our most basic assumptions about how galaxies are born, live, and die, presenting us with paradoxes like Dragonfly 44, a galaxy with the mass of the Milky Way but almost none of its stars, and NGC 1052 DF2, a galaxy that appeared to defy logic by having no dark matter at all. Through their silent testimony, these dark galaxies have become our most powerful teachers. They are the natural experiments that test our grand cosmological models to their breaking point, revealing both the stunning accuracy and the curious gaps in our theories like lambda-cold dark matter. They show us that galaxy formation is not a single story but a spectrum of possibilities, from primordial failures like Segue 1 to galaxies quenched by their violent environments like VCC 1287 in the Virgo cluster. They hint at a universe far more dynamic and violent than we imagined, where galaxies are constantly torn apart and rebuilt by tidal forces, and where even the smallest, faintest dwarf can be the surviving heart of a vanquished giant. In their profound darkness, they illuminate the invisible architecture of the cosmos, mapping the distribution of dark matter and revealing the hidden scars of the Milky Way's cannibalistic past. This journey into the shadows doesn't offer neat answers. Instead, it opens deeper, more thrilling questions. It invites us to wonder about the true nature of dark matter, to speculate about the possibility of entire galaxies made completely invisible, and to reconsider our place in a universe where the visible splendor of stars is merely the glittering fringe of a vast, unseen reality. These 25 dark galaxies are a testament to the fact that discovery is not about closing books, but about opening new and darker chapters. They remind us that the universe's greatest secrets are not always written in light, but are often hidden in plain sight, waiting for our curiosity and ingenuity to bring them into focus. So we turn the question over to you. Which of these dark galaxies captures your imagination the most? Is it the enigmatic Dragonfly 44, a ghostly giant made almost entirely of dark matter, the controversial NGC 1052 DF2, which seemed to break all the rules? Or the ancient Tucana II, a pristine fossil stretching far beyond what we thought possible? Share your thoughts in the comments below and let us know which cosmic mystery you find most compelling. Remember to stay curious, because the universe is always holding its deepest secrets just out of sight, in the beautiful, terrifying, and fascinating